Okay, Xiaowei, yeah, the floor is yours.
Okay, good morning, everyone. So, thanks to the previous 2 weeks, she talked about a lot about the atmospheric turbulence and general rules in the related to our meteorology direction. Today, I will talk about the computational fluid dynamics. So my background from the fluid dynamics direction, especially the mechanical engineer direction. So we are more focused on the how does the research on the turbulence, what's the turbulence in the general mechanics domain. So let's start from the conception of the computational fluid dynamics. So part one will be computational fluid dynamics. We call CFD part. So the computational fluid dynamics, I'm not sure how many of you has already have this course before. I assume all the members maybe have the fundamentals for the fluid dynamics and heat transfer. So computational fluid dynamics is the science of predicting fluid flow, heat transfer, and mass transfer, and also the chemical reactions and related phenomena by solving the mathematical equations which governing the process using a numerical process. So the fundamentally actually is solve the equation with the numerical method. So the results of CFD can be used in the conceptual study of the new designs, detailed product development, and troubleshooting and redesign. So when I talk about the troubleshooting, redesign, and product development, so fundamentally it's still in the manufacturing direction for the mechanical engineering. For the general civil engineering and also the meteorology direction, we are fundamentally use computational fluid dynamics for the prediction. Prediction how does the flow transport, the heat and energy in the environment. So CFD analysis complement the testing and experimentations. So it can reduce the total effort required in the laboratory because simulation is relatively easier to conduct than the experiment. So and relatively cheaper than the general experimentations. So let's talk about the where the CFD is located. So CFD fundamentally is a modeling and a simulation. So it's an interdisciplinary of the applied mathematics. Let's see the figure. Applied mathematics, engineering, biological and physical science, and also the computer science. It's a middle intersection of this area. So in the interaction, actually we call modeling and simulation. To be specific for the CFD part, it's a interdisciplinary research of the fluid mechanics, computer science, and the numerical method. So we are using the numerical method and also use the computer technique to solve the fluid problem. So for this course, I will focus on talk about how the CFD works. So once we understand how the CFD works and how the CFD procedures, so you can understand what happens with CFD approaches. So I will use this geometry, this figure to talk about the. I will use this geometry figure to talk about the procedure of fluid mechanics, CFD. So fundamentally, CFD we have three parts. We have pre-processor, we have the solver, and also the post processor. So in the pre-processor, we usually have the geometry, we have the mesh, we have boundary conditions, and we have equations, initial guess, solution, solve the equation, and also get the results of results analysis. So we have 7 steps. So for most of the software, actually software has already solved most of the problem. For example, if we are using ANSYS Fluent or other software, it's already developed the solver part. So it's the CFD software. What we need to do fundamentally is the precursor and also post-precursor. So even we have the homemade software, but it's the solver part is already there. We can go inside the solver to make some modification, but fundamentally we need to be clear with the first three parts: geometry, mesh, boundary condition, and then we use the CFD solver to solve the problem and get the results. What we need to do is do the post-processing. So I will use one example to talk about how the CFD works. I think for most audience today will be this two theoretical and two mechanical engineering direction. But I think this example is very well to explain how the CFD works. Once we understand how the CFD works, and it's easier for us to understand how do we use CFD in our simulation or in our research. So the problem I talk about today actually is a 2D problem, heat conduction problem. For example, here the problem itself is talk about that we have a plate. It's a 2D problem, and the temperature. The temperature in the three boundaries is T1. So this means in left bottom and the right temperature T1 and the top temperature is T2. So what we know is we know the conductivity key. We know the length is 1 meter, width is 1 meter, and the T1 is 100, T2 is 500. So the problem is we want to get a distribution of the temperature inside this area. This is a very traditional engineering problem about the heat transfer. So after we see this problem, we think about if we are using CFD part, we follow the procedure we talked about before, but I reorganize the procedure a little bit to be easier to understand. So for the procedure, let's start from very beginning. The step one, we define the control volume, or the generates the mesh grid. It's the same as the geometry. If we are talking about something, some people talk about the geometry design and the generation mesh grid. It's same definition. So we start from the control volume and generate the mesh grid. Here, because the research area is displayed, so it's relatively easier to think about the control volume. We will be with ourselves, and the geometry and the mesh grid, we will divide it by this geometry to several pieces. For example, here I'm using the uniform mesh grid. I'm picking the delta x equal to delta y, and totally we have 6 grids. So totally we have 6 by 6 grid. It's 36 grids in this domain. So fundamentally we are dividing the computational domain to with the uniform mesh grid to 36 grids. And we have, for example, we have the 6 grid in the x direction, 6 grid in the y direction, and we can give a number to each grid. So this is step one, generation the control volume and generation the mesh grid. And then we come to the discretization. Yeah, this part is I especially take the discretization here is because I want to make the equation and the equation system to be resolved with numerical method. It's very important. Talk about the discretization. Fundamentally, is dealing with the equation system. For example, so we will not do the review about the equation, but generally, if everyone have already know the heat transfer equation, we know the heat transfer equation will be this equation: partial T partial x squared equal to 0. This is the steady heat transfer 1D heat conduction equation. And for the 2D heat conduction problem, we have this kind of equation: partial U partial x squared plus partial U partial y squared equal to 0. So this is the equation. This is the equation governing this system. This means for whatever physical problem we are encountering, we have some governing equation. This governing equation comes from our knowledge level, just like when we learn the heat transfer problem or we learn the fluid mechanics problem, we know something, what's the governing equation there. So the governing equation for this specific question is the partial u partial x squared plus partial u partial y squared equal to 0. So I will not go through the review process, but whatever happens, you can find the equation for the equation system. So after we talk about CFD, fundamentally is we are using numerical method to solve the physical problem. Fundamentally, we are combining the fluid mechanics, heat transfer knowledge, and we will use numerical method to solve this equation. So I will talk a little bit numerical method, just a quick review. If I'm not sure how many of you had already taken numerical method class, but if not, but this is just the general talk about how does the numerical method works. Here, I will specifically introduce the finite difference method. So finite difference method is a class of numerical techniques for solving the differential equations by approximating the derivatives with finite difference. So for example, in this figure, I talk about derivatives. The sensitivity to change of the output value with respect to a change in the input value, we call it a slope. For example, in this figure, the y-axis is the temperature, x-axis is the location of x. So the slope, actually the change in the t divided the change in the x. So we call delta t over delta x. So this means the dt dx, we can represent as t I plus 1 minus ti divided x xi plus 1 minus xi. So this fundamentally, if we are using this kind of the approximation, we are talking about finite difference. Because of the slope or the derivative along this curve actually changing with location. So we are using some average value to approximating the real value. So this is what we call finite difference. And to be more details, for the finite difference, we also have several approaches. For example, the first figure, the left figure, is talking about a forward difference. Forward difference is we are approximating the slope in this location with the value of this position and the next point of position. For example, here, dt dx equal to t temperature I plus 1 minus Ti divided by the delta x. So this is forward difference. This means we are approximating the slope of this point from the right side, from the forward information. Similarly, we can approximate the derivative in the backward, just like we are using information in xi minus 1 to xi. So if we approximate the dt dx equal to ti minus ti minus 1 over delta x, so fundamentally it's a backward difference. We are approximating the derivative in this part. But from these two figures, we can see clear if we are using the forward, if we are in forward approaches, the true slope is the black line. But if we are using the forward approaches, fundamentally we get the slope is the red line. So this means if it is clear, the red line have a bigger slope than the true slope. So this means we get a little bit larger value than the real value. For the backward difference, the black line is the true value, and the red line is the approximate the slope. So we can see we get a little bit smaller value than the true slope. Okay, so the scientists in the CFD direction actually they developed other schemes to make the finite difference works better. For example, here this figure, we can see if we approximate the derivative of the temperature in this location with the Ti plus 1 minus Ti minus 1 divided by 2 delta x. Fundamentally, you can see here, the black line is still the true slope. The red line is the approximate slope. And in this figure, we can get it's intuitive to get a sense that the red line is have a relative very similar slope as the black line. So if we are using this approach, we get a much smaller errors than before. So there are many error analyses we will not go through in this class today, but fundamentally, when we talk about the forward difference and the backward difference, it's in the error is in the order of the delta x. But if we are using a central difference, the error is in the order of delta x squared. So actually, this is very make a very big difference, because usually our delta x is very small. Think about the delta x is 0.1. So this means that the first two approach, the error is in the 0.1 order, and the central difference is in the order of 0.01 order. So it's much smaller error. So this means that in the future, we prefer to use the central difference in the example we are talking about today. So if we use, once we develop the understanding of the finite difference, so we talk about from the first order to the second order derivative, because we know for the heat transfer equation, we have second order derivatives, and in the fluid mechanics class, we have the Navier-Stokes equation. We have the viscous term is in the second order derivative, and we have the convective term also is the second order derivative. So second order derivative is a lot. So if we are using this idea to represent the finite difference method to the first order to the second order, this is a figure we are talking about. For example, here we talk about the first order in the position of xi minus 1 over 2 and xi plus 1 over 2. So we talk about the derivative in these 2 points first. So for the first point at xi minus 1 over 2, the derivative is equal to ti minus 1 divided by delta x. And actually, even I'm dividing with delta x, but here actually we are using the central method. The order, the error is in the delta x squared, because you can see we are getting the first derivative using information of the forward point and the backward point, so together. So we get the central method for the first derivative, and we get a central method for the second derivative at this point. So this means for the first order level, we get the error is in the delta x squared. And for the second order part, so for the second order, we use the finite difference again, central method. For example, if I want to get the dt dx squared at this point, I'm using the first order derivative in the xi plus 1/2 and xi minus 1/2. Fundamentally, then we are using the central method for the first order derivative to get the second order derivative. And after we convey all the information together, we get this kind of expressions. It's a dt dx squared equal to ti plus 1 minus 2ti plus ti minus 1 divided by delta x squared. So this means this formula now is discretization of the original formula we get the 2D heat conduction problem. So this from first order to the second order. And then because we have a 2D problem, so we need to have a 1D problem to the 2D. So fundamentally, previously we have 3 points in the x direction. Now we have 3 points in the y direction. This means, okay, we have the subscript, we have 2 numbers, I and g. I will for the x direction, g will for the y direction. And this is what we call the 5-point scheme. So we can get the dt dx squared actually is the formula we get in the previous page, but you can see that we fix the y direction, only changing in the x direction. And the dt dy square is something related to the y direction, 3 point in the y direction, but not really related to the x direction. So this means we can extend our understanding from a 1D problem to a 2D problem. If we have this knowledge, it's easy to extend to the 3D problem. For example, we have I, G, and K. We have three dimensions to talk about. So, but when I get the whatever the first order derivative, second order derivative, we will use the relevant point to represent a value with different points. So to be a summarization of what we get for the equation and the discretization, this is the system. Fundamentally, we have the equation for the 2D heat conduction in this part, partial t partial x squared plus partial t partial y squared equal to 0. And we discretize this equation to this kind of representation, and the y direction equation to this representation. So we get the finalized discretization equation for the system. So we call this equation now. This equation is the governing equation for our heat transfer in the 2D plate. So any questions so far about the equation part? So we get the fundamentally get the geometry, or someone called it control volume, or the computational domain, and we do the mesh, and we do the discretization. So we translate the equation to the discretized form, which can be solved by the computer. So after we define all the precursor, this means we have already get the equation system, we have already get the control volume, and we have already get the mesh. So we come to the second part of the procedure in the solver. In the solver, we need to do what we need to do is define the boundary condition. For example, for this equation, it's relatively easy to understand the boundary condition. We know the temperature in the left bottom and the right is 100. So, and the top boundary is 500. So I'm using the red color to talk about the known boundary conditions, and I'm using the green color to show the points we don't know the value. So the goal of this problem actually is we want to use the known boundary conditions to solve the unknown points inside this grid. So we come to determine the equation system. So what does it mean, the determine equation system? So determine equation system is we have already get the discretized equation. We want to solve this equation. What do we do? Fundamentally, you can see that's the formula here. For each grid point in the green color, for example, in this point. So we have the equation like this one. We have like the equation. This is the equation we get before. So if we have already defined the mesh geometry is delta x equal delta y. So this means the equation system is now come from like this kind of representation. Is relatively simple version of the equation above. If we are using the non-uniform mesh grid, this means the coefficient in each term maybe changes, but fundamentally the equation system we can still get the equation system. So this is the equation we get for the system, and for this specific point, for example, I talk about the theta 10. You can see this equation tells us the temperature in this in each specific point is related to the 4 grid point around it. So there's a relation between them. So this means the temperature below it, the in front of and the in front, left, right, top, and the bottom, and 4 times of itself, it's there. This is actually the representation of the heat heat conduction equations. And if we translate this one to our scheme here, this means theta 10, theta 9, 11, 6, and 14 minus 4 times theta 10 is equal to 0. So here theta and t actually the same definition. Just use theta to represent the t. It's easier to understand. So this we get the equation for the theta 10, and once we get the equation for theta 10, this means we can get the equation for every 16 terms. So we go to the step 5. We set the initial condition. So fundamentally we have 16 unknown, theta 1 to 16. We need to initialize the simulation. We need to have initial guess. For example, here I'm guessing the initial temperature is random number from 200 to 500. Whatever number we get, we just assume it's random numbers. And after getting random number, we need to solve the equation. And we make sure it's converged. And if it's converged, we go to the results analysis. It's not converged, we will need to repeat the initial values, initial field, and use the iteration method to make it converge. So this is how does it works. So we know the theta 10. Let's take the theta 10 as an example again. We know the theta 10 is equal to theta 9, theta 6, 11, and 14 divided by 4. So this means we can have the iteration 1 is we get the theta 1 at the iteration 1. We get it's 200, 100 plus 100, and theta 2 and theta 5. When I use the superscript here, actually talk about iteration, it's not the power. So if we are using the theta 10 as the example, theta 10 at iteration 1 is equal to theta 9 at 0, theta 6 at 0, theta 11 at 0, and theta 14 at 0. Because we have already got the initial value. Initial value fundamentally is the initial guess. So this means we have the 1, 2, 3. We have these 4 temperature already. We add them together and divide it by 4. We get the theta 10 at the iteration 1. So this is just from the initial value to the iteration 1. And we repeat this method. We repeat these approaches for several times. For example, we can get the equation iteration k plus 1. So this means we repeat many times. We always get theta 10 k plus 1 equal to theta 9, 6, 11, 14 t divided by 4. So this approach, this means we can make a iteration to go to many times. So and because this equation is from the heat governing equation, so fundamentally this equation is represented the equation governing the system. So we are using this equation to filter the initial guess many times. So this means after each iteration, we expect the values actually is more accurate than before, or the value is more close to the real value. So we are approximating to the true solution. So when we do the iteration never stops. So we need to define a criterion for the iteration to stop. So if we define maximum, so usually people define the criterion is epsilon, just like the arrow. So if we define the maximum value of the theta I minus theta I k plus 1 divided by minus theta I k is less than some criterion, we assume it's converged. This means we have initial guess, it's not converged at the very beginning, but after several simulations, the value is more and more accurate to the true value, and we define if the value is close enough, we stop the simulation. So the epsilon actually is the criteria we defined in the system. So after this one, after we get everything, so we want to solve the equation. If we don't have software, we need the coding by ourselves. For example, because this equation is very relatively simple or easy, so we will develop a coding with MATLAB. For example, if I started with MATLAB coding, we talk about the boundary condition first. We have two boundary conditions, T1 and T2, 100 and 500. And we have the initial condition. We have theta. Theta is for theta. We have 16 points. It's unknown. What I did is just give random number for this theta for 16 numbers. But for defining the initial guess or initial values, it's better to think about the physics problem again. For example, in this problem, we know the three boundaries. Actually, we have 100 and 500. This means the temperature in the green box fundamentally should be between 100 and 500. It cannot be beyond 500. It cannot be 800 degrees. This starts from the sense of the physical sense of the problem. So if you are defining the initial guess more close to the real value, this means our simulation can get the convert much faster. If you are guessing it's far from what we get, probably it take a longer time for the simulation to convert. So here, this is the initial guess I get. So after we get this one, you can see we mix the code. We get the for loop for the I is equal iteration is equal to 1 to the iteration time step. We define the theta one is equal to some values, and it can be represented in the formula here. Fundamentally, talk about the theta k plus 1 is have some relation with theta k, and if the criterion is touched, just like if the error is less than the criteria we defined, we stop the simulation. Fundamentally, this is what I get when we solve this CFD problem. Let's take theta 10 as example again. So the initial value of theta 10 is 150 degrees, and after one iteration, you can see it goes down to 129, and then goes up again, and goes up, and we can see from this figure, we can see from this line, the value actually is closer to the 236 or 237. Fundamentally convert some value. This actually is fundamentally how does the CFD works and how does it get the values. And then finally, we do the process. Step 7 is the result analysis. So this means in this problem, we get the problem is we have the 3 boundaries and 4 boundaries with 100 degrees in three boundaries and 500 in one boundary condition. We get the results like this one. We get the temperature lower in 3 boundaries is equal to 100 and 500 at the top, and the distribution in the middle. So this is the general procedure of CFD simulation, and we use this procedure, we can solve any problem we encountered. So because we are talking about the simplified version problem, so this means okay, the real world problem may be more complex, but even complex, we can use a similar procedure to deal with the problem. For example, if we talk about this is equation we have today, we get the finite difference representation as this formula. And if we have the heat source, this means, okay, we in this equation, we will have another term called phi. Phi represents the heat source everywhere. And if it's a non-steady state, if we have another term is talk about a partial T, partial temperature, partial the time. This means, okay, the temperature may be changing with time. So this means along with this line, we are solving the 2D problem for the steady state heat transfer problem, but it's easy to expand to the unsteady state and with the heat source and also to the 3D problem. fundamentally use this approach, you can solve every heat transfer problem we encounter. And if for the general CFD problem, we have a little bit more complex situation. We have not only the heat equation, but we also have the mass conservation and the momentum conservation. We have already learned this equation in our fluid mechanics class. So we have the mass conservation represented how the rho is changing with the domain, and we have momentum equation to represent how the UVW velocity is changing in each direction, and we have the heat equation, or someone called energy equation, is change how the temperature changing in the computational domain. Today we are using the example of this equation to solve the heat conduction equation, but fundamentally, if we are encountering a problem with heat transfer and turbulent flow, is the same procedure. But the situation is we have more complex system. It's not easy to coding. So this means sometimes we will have software to help us to solve the problem, or we based on some homemade solver. So this means fundamentally the solver is already developed for us to solve this kind of equations. So far, any question about the CFD, general CFD procedures?
I have a quick question about the slide you had before this.
Yeah, this one?
Yes, the last one, the non-steady state. Perhaps
yeah.
You can briefly talk about how we can link this non-steady state equation to the energy balance received by a surface of this plate or a surface of a three-dimensional volume.
How do we link this equation to the analysis?
Yes, so it's more toward urban climate research, right? So for example, if we only consider the roof of a three-dimensional volume, for example, a building, this roof will have its own surface energy budget. So it has incoming radiation, outgoing radiation, and it also emits, the sensible heat, latent heat. So the residual term in this equation is the heat conduction into the surface. And how we can, add this conduction term into this non-steady state to solve for the temperature distribution within the solids.
Okay, yeah, I think this is a good question to my understanding. So maybe she can correct me if not correct. So my understanding is in the computational domain, just like with computational domain, we are developing. Let me find a computational domain. For example, for this domain, think about this our computational domain. So that equation is solved in each grid point. So that equation solved in each grid point. So if we have a building here, the building may pick some points. So to my understanding, to solve the CFD simulation, that grid point, if it's a building, this means okay, the heat flux that will be passed into the building. And if that grid point is in the fluid, this means the heat flux pass to the fluid. So this means in the CFD procedure solve the problem. And also again, that make it more clear. This is very cost resolution, but if in real case, it's very fine resolution. So this means we can use the sand descent function that help us to get the we can define function, find the interface of the building roof and the fluid. So whatever the point is located on the roof, so we can define the points located in the roof and located in the just above the roof in the fluid. So the heat exchange between these two actually what the heat flux you are mentioning about. Do you have some comments?
Yeah, I think if Chenghao, if I understand your question correctly, you are asking how we can impose a more realistic boundary conditions.
Yeah.
Right, for if we're thinking about this heat transfer problem. Yeah, so just speaking of it from my limited understanding of, let's say, the urban canopy model, I think in the partial differential equations you solved in the urban canopy models, the heat conduction equation is one of them. And so, for example, if you're thinking about applying such numerical schemes that Xiaowei has talked about, all right, I think all the numerical methods and also the discretization would follow basically exactly the same as what's shown in the slides, except that in the boundary conditions, you will need to be considering the so-called mixed boundary condition, where the it's a mixed between a flux boundary condition and a temperature boundary condition.
Right.
And so I think there is a way that you can maybe write your surface energy balance and then incorporate that specific mixed boundary condition into the into your numerical solver. That's my understanding. Yeah. Which I think probably you're currently doing that, right, with your students. So
yes. Yeah, he's online. It's just so that students who are not familiar with CFD know that these boundary conditions, we can not only specify initial temperature as boundary condition, but also flux as boundary conditions, both temperature and flux.
Okay, so fundamentally we have three types of boundary condition. If we use the terminology of heat transfer, we have constant temperature, constant heat flux, and also the convective boundary condition. So fundamentally is so in that scenario, I'm thinking about your, if my understanding is correct, so your building roof will be the red color in my figure. That's define some values in somewhere.
Mm-hmm.
Is that right? Yeah.
Yeah.
Okay, nice, thank you. So let's move on to further. Any other questions or any other discussions? So again,
hey, Doctor, I have a question.
Yes.
Yeah. The previous slide. Can you go back to not this one, the previous one? Okay, this one is good. So, is there any other way that you can define, for example, define the temperature? I see in this mesh, in this discretized mesh, you define the temperature in every intersect point. So can we define the temperature, for example, in the center point of this grid?
Yes. Yeah. Okay. Yeah. This is a very good question. So I think you should talking about the discretized method. That's like the yeah. I'm defining the temperature in the just like edge, right? We can still define the temperature in the center grid. So if I'm understanding correct, this is your question, right?
Yeah.
You're talking about if we can define the temperature in this point, right?
Yes.
Instead of the boundary. Okay, that's a good question. So okay, think about a scenario. So go to the extreme value. That's like if my mesh is fine enough, that's like I have infinite number of mesh. So many mesh. So fundamentally, the limit will be this point and this point will be. This means we increase of the mesh is very similar, or close limit is the same point. So this is the general things about this problem. But you are right, in the realistic, actually we define in the middle point. That's possible.
Are you still there?
No,
I mean,
Does this answer your question? Yeah.
Yes.
Yeah, I mean this one is showing the example. We don't differentiate the difference of the edge or the center, but in the real cases, actually we define the problem. But whatever happens, it's we can define the value at some points to represent the geometry. For example, for the roof, just like what Chen talked about, if we have a roof here, definitely we have some grid points. So this means the grid points and the geometry of the roughness of the roof need to have some relations. For example, if inside the roof, definitely we just define it's the in the center is 0, but at some point maybe it's in the boundary, so it's better to define in the boundary. Yeah, this depends on the problem.
Okay, I got it. Yeah, thank you.
Xiaowei, do you want to also briefly talk about the configuration in LES, like how
yes,
like better configuration?
Yeah. So, you mean now? Let me. Chen, can you repeat that question again? Yeah.
Oh, I mean in LES we can both have the grid cell within the the center of each grid or at the boundary of each grid, something like that.
Oh yes. So in the large area simulation, so fundamental, I'm not sure. So I think my group and is using the Let's Go. Chen, do you group use Let's Go also?
No, we haven't started yet.
Oh, okay. So fundamentally, I don't have slides for it. Probably I can quickly draw a figure here. So for example, this is surface, and this is our mesh grid in Z direction, and this is grid in the X direction. Fundamentally, this is the y direction called Z. So we are storing this is called what I call center point. This is what we call the edge point. So fundamentally, the UV pressure is in the center point, and the W is in the edge point. The reason why do we do this way? Because again, it comes back to the problem we talk about, the center method. We just mentioned center method. For example, you can see this is this direction Z. So the du dz, we care about the tau is mu du dz. So this means if we are defining the UVP in the central nodes, when we do the derivative, actually tau is located in this edge again. So this means tau will be in the edge, and we make sure it's using the central method. It's the second order accuracy, and we do the derivative of W. We will come to this point. Fundamentally, this tau equal to mu d fundamentally our flux. So this means that we get the flux fundamentally is in the second order. This means the dirt square is order of that square error in this part. So this is what we do in the Let's Go code. We talk about the central method and the edge method. Fundamentally, this method is represent the errors. We want to keep the error in the second order, not in the first order. Okay, I'm not sure I answer your question. Not yet related to large area simulation, but it's more general related to the error. So this means every time we define the location of the points, is talking about the error. We want to reduce the error more for the CFD direction. Okay, let's move on to the second part of my talk today with turbulent flow modeling. So turbulence is encountered everywhere. So this is examples for the vortices visualized with laser fluorescence, and also turbulent vortices separating from a cylinder. So we have this kind of turbulence. And the first one I talk about what's the turbulence, and Chi has already mentioned, and many of you have already taken the course. It's unsteady. It's a periodic motion in which all three velocity components fluctuating, and it's mixing the matters, mixing the momentum and energy. So we usually decompose the velocity into the mean and the fluctuation part. This means, okay, the velocity actually is always fluctuating. It never stops fluctuating. It has some values. It's fluctuating around some value. So, but the similar fluctuation for the pressure, temperature, and the special concentration values. Okay, so fundamentally, how do we define turbulence? We use Reynolds number a little bit. But not a little, we use Reynolds number to define. So if Reynolds number is very small, we come from a laminar flow, and we have some laminar separated flow, laminar separated periodic, and also we have the laminar separation and turbulence weak periodic, and if the Reynolds number is big enough, actually we have turbulent separation chaotic. So this means Reynolds number is very, very important in our research for the turbulence to define where the turbulence happens. And these are some examples is from the experiment. They take the picture of the Reynolds number, different Reynolds number. We have smaller from 9.6, 13.1, 26, and you can see from this one for the Reynolds number is 10,000. It's almost the turbulence. It's chaotic anymore. So so the next following question is how to represent turbulence. So because turbulence is chaotic, we cannot give an exact function to represent the function of a specific point. So, but the people found, okay, actually we can represent the turbulence with time mean or the domain mean. For example, here time mean actually is the mean to the average on the t minus 2 over t and t plus 2 over t. That's like in the domain, in the time range, we do the average, and we can also do the average in x direction or in the volume. Just like the volume. Talk about the average sense, turbulence can be represented with a formula. And this come back to the definition again, fluctuation. This is the most important for the turbulence part. So if we define F actually equal to F bar, when I talk about F bar is the time mean of the quantity, F bar plus F prime. So F bar actually the time mean, and fluctuation is the real value minus time mean. So according to this definition, we have the U is equal to U bar plus prime. P is equal to P bar plus P prime. So we have already mentioned we have the Navier-Stokes equation. We have mass conservation equation. We have the Navier-Stokes equation. This is for momentum, and we have another equation for the temperature. I didn't write the temperature equation here. And we have the equation for the species. For example, we have the ozone concentration all over the atmospheric turbulence. We know the concentration of air contaminant. So we have so this means how many species we have. We will have how many equations. For example, here we have if we talk about the momentum, we have the equation for the mass conservation and the momentum conservation. Because momentum conservation is three-dimensional, so this means the second equation here actually is can be in three directions. This kind of UVW. So here we have four equations, and these four equations we have four unknowns. We have the U, V, W, and the P. So we have four unknowns and four equations. This means this system can be resolved with the solver we mentioned before, and we get because it's the four equations and four unknowns, we get exact answer for each grid point. So if we have temperature involved, we have one more equation. We have one more equation, but we have one more unknown is temperature. Again, also for the concentration of different air contaminants. Each time we have one species, we will have one more equation. So this means we keep the equation system always can be resolved. So when you do the time mean to this equation, we get the mean equation for the mass conservation. You can see here is partial ui partial xi equal to partial ui partial xi. We get the equation for the mean equation for the mass conservation and the fluctuation equation for the mass conservation. The same story when we do the time mean to the Navier-Stokes equation. We get this kind of expressions. Okay, there's a long procedure. We do the average to this part, and we get the equation for the mean equation for the momentum. You can see here is partial ui. So everything is with bar, but we have one more term appears here. This is what we call the renal stress, and I think it's a very important term. A very important term for us to understand the general atmospheric turbulence. So this part is come from the average processor. So if this means if we are don't do the average, we don't have this term. Now we have to the average equate to the equation, we get this term out. This means this term is coming from the averaging process. So now the problem comes. So before, for this equation, we have 4 equations and 4 unknowns. Now for the filtered equation or time average equation, we still have 4 equations, but we have this UIUG, we have 9 more terms. We don't resolve it, just like we represent, we give new variables, but we don't have equation for it. So we need to closure the equation. We need the equations closure problem. Just like we need to find 9 equations for these 9 terms. This 9 term is coming from time average, but we don't have formula for it. So we need the formula to represent it. So this comes to the closure problem. So in order to make the turbulence closure, so we have several approaches. Fundamentally follow this line. We have 0 model, 1 equation model, 2 equation model, and a large eddy simulation direct. We have so many. So for example, let's talk about the RAS part. So we want to represent that part. So the term we're talking about here, renal stress, is in this dashed line. So we need a 0 model, 1 equation model, 2 equation model, or something. So this is RAS-based model. This means we need models, and to be more accurate, actually we go to the large eddy simulation and also go to the direction numerical simulation. So let's talk about this simulation approach a little bit. So for example, to closure the RAS model. So RAS model equation required to closure for the renal stress. Fundamentally, it's RAG. It's called UIUG. If, for example, people usually model like this one, it's a rho 2/3 T and delta RG, and also nu T, and with some kind of the mean quantity. Here, capital U means the U bar, the mean quantity. So this means that this equation is try to link the renal stress with the mean quantities to represent what happens. So this term is nu T is turbulent viscosity is indirectly solved for the single transport equation of a modified viscous for 1 equation mode. For 2 equation mode, means we not only represent this equation, we represent another equation. We introduce the TKE equation. We have a TKE equation to solve it. So the transport equation for the turbulent kinetic energy and the dissipation rate are solved in the turbulent viscosity solved. So the turbulent viscosity can be computed for the RAS equation. So we have the key actually is the UI divided by 2 and the dissipation rate of turbulent kinetic energy here. So this is the modeling for the 1 equation, 2 equation, and the renal stress. So for example, there are many equations. This is just one example. We talk about the nu T is equal to this kind of definition. definitely we can have the new T have different model, but the new T this people use very popular one, and the additional variables are function of the modified turbulent viscosity and the velocity gradient. That's like people want to make the model more and more accurate to represent the truth. So we need more and more accurate model for the new T. So we get a more and more accurate model for the new T representation. And for example, this specific equation is designed specifically for the aerospace application involve the wall bounded flows. So our turbulent environmental turbulence actually also belonging to the wall bounded flows. So for example, here especially for the turbine machinery and the boundary layers with adverse pressure gradient. And so here we also need to think about the mesh. Can we use a coarse fine mesh grid as the wall? So the mesh and the wall very important. We talk about the mesh of the wall later. Let's finish the modeling part first. We modeling the Reynolds strength term. So for the two equations, so the turbulent kinetic energy comes. So we have the convection, generation, diffusion, and the destruction terms. Dissipation rate formula can also be from mass conservation equation. We get this kind of equation. Mass and the momentum equation. We get one more equation for the turbulent kinetic energy. So we resolve this turbulent kinetic energy and our model equation and also the Navier-Stokes equation. This fundamentally we are using the two equations. So we have the baseline model, and also we have a more complex model, a semi-empirical model. We key epsilon. We have a key model and the epsilon model, and it's valid for fully turbulent flows. So far, the two equations for valid for fully turbulent flows. If we are talking about the transition flows, it's not valid. So it's reasonable accuracy for the wide range of turbulent flow in the industry, heat transfer, and our environmental direction. So here the table talk about the comparison of advanced turbulence models. So we have the Amorous model. It's a typical one equation model. We have standard K epsilon model. We have the ING K epsilon model. We didn't mention here. Think about the ING K epsilon model and the reliable K epsilon model. Actually, is we make the K epsilon model more state of the art to represent the term more accurately. Fundamentally, we are still modeling the UG bar prime. Yeah. So we talk about a RAS mode. Time mean actually is RAS mode. Now we talk a little bit about large eddy simulation. So large eddy simulation model, large eddy simulation fundamentally is reasonable for transport of momentum, equation, energy, and other scalars, directly affecting the mean fluid. So here one idea is anisotropy. Anisotropy is very important. So our model actually is subject to the history effect and the flow dependent, strongly dependent on the flow configuration, boundary condition, and the flow parameter. So the smaller they tend to be more isotropy and less flow dependent. But the large geometry is more likely to be affected by the boundary condition. So this means if we have a mesh width fine enough to resolve the Kolmogorov scale, just like the smallest eddies cells, we are doing the DNS. Actually, we can assume all turbulence isotropy, but we cannot get the very fine resolution because our computational resource is not enough. So usually we can only resolve the large eddies, but not the small eddies. So this means people propose to use LES. So the LES directly computes the resolved eddies or the large eddies and model the small eddies. We call subgrid scale modeling. So there's some relation between the large computer effort to do the number of grid points and the Reynolds number. Fundamentally, this figure shows how the DNS and the large eddy simulation. So we know the turbulence have structures, have large eddies, small eddies, and very close to the wall. This is our urban environment or the building in this region. So we have very small turbulence. So we have large scale eddy to small scale eddies. So the inject of energy is flux of energy to the dissipation of energy. If we resolve all the details, just like we resolve all the equations, actually it's direction numeric simulation. This means, okay, if I'm solving these equations, fundamentally I'm running the direction numeric simulations. And as we mentioned 10 minutes ago, if we resolve the time mean equation, we get the range equation. Now we are talking about the third approach, is large eddy simulation. Just like we are not time mean, but we are doing the average in the spatial, but resolve the big structures and model the small structure. This means here we have the Q5 tilt. So the tilt actually is just like we use the G function to multiply that convolution with we pick a filter. The filter is G. We use this filter to filter the velocity field or some other field. We get the Q tilt. So this means, okay, when we talk about bar, actually time mean. When we talk about tilt, actually we have a filter on the domain. So this is tilt. So for the large eddy simulation, we do the filter of the mass conservation and the momentum conservation. We get this kind of the equation. We get the filtered equation is partial u partial xi tilt equal to 0, and we get the filtered momentum equation like this one. Don't be confused with the filter and the time mean. Time average, we get a bar, is very similar, but the difference is for the range equation, we get the everything time mean, and we get also we get a term we call the Reynolds stress. But here we get the filter of the equation. We also get the term here. It's not Reynolds stress, but very similar to Reynolds stress. We call subgrid scale stress. So this means this term we also need to model. Similar as the Reynolds stress need to be modeled with the mean quantity. We model the subgrid scale part of this part to close the large eddy simulation model. So this represents the related topic will come to the subgrid scale modeling, how to model the subgrid scale turbulence. Fundamentally, there are also many equations. There are many approaches. Let's use the most simple one. It's talking about the tau Ig is equal to the filter size and also strength tensor. There's some relation between them, just like that. Okay, so we can resolve the Sig strain rate tensor can be represented by the filtered quantity. So this means we know the Sig tilt at each grid point, and we know the grid size. We know what the tau Ig looks like. To be a summary of this equation system, we have one mass equation for the pressure, 3 Navier-Stokes equation for the 3 velocity component, and a 9 subgrid scale momentum closure equation for the subgrid scale quantity. Similar as RANS, in the RANS we have 9 Reynolds stress model. We have 1 equation, 2 equation, and also more complex closure. For the large eddy simulation, we are same. We will have the this general Samogronski model. We have also a dynamic model, scale-dependent dynamic model. We have more and more advanced model to represent this subgrid scale terms more and more accurate. So this general talk about the DNS, the LES, and the REST relation. So because we are running a simulation for our interest, we are talking about flow over the urban. It's just like the flow over the urban. It's very near the wall. And the last, as mentioned, in the first course, we are very interested in the near wall region because all the formula, morning of curve, and other equations come from the surface layer. Fundamental surface layer is roughly 100 meters above the ground. That's very close to where we are living. And here is most of momentum exchange here, and it's exchange here. And the vertical gradient are very big. So we are very clear about what happened in this region. So in the near turbulence, it's very important. So we need some specific treatment for the near turbulence. So most of the key episode and the ISM turbulence model will not predict cracked near the wall behavior if generated down to the wall, because we have the, you can see down to the wall we have the log law and also the viscous layer, but our simulation is not fine enough to capture the viscous layer. This means we cannot represent the viscous layer very well. So we need to give a model to the wall. So usually we need a special near wall treatment, and sometimes we have the standard wall function, non-equilibrium wall function, and some two layer model. Yeah, it doesn't matter about the many wall functions, but the idea is, okay, near the wall we need some special treatment because our grid resolution cannot capture the change in the y direction, because now we have very sharp, very high DUGZ in the first two grid points, but our resolution cannot capture these changes very well. So for the main equation, for example, so let's only talk about the momentum. For the momentum, usually we use a general log law U star. So we define the U star and represent the U star with the wall model. That's what we treatment for the U star. For the temperature, here is one of the representation. But she also mentioned before we can use morning over curve. It's similar as the equation for the U star. We have a theta star or the concentration star. That's like whatever happens for the momentum, for the temperature, and also for the each species, water vapors and air contaminant, we need to have a model for it to represent the accurately represent it near the wall or near the building. So here is a comparison of the general wall treatment. For example, we have standard wall function. It's popular used, and we have non-equilibrium wall functions on two-layer models. We didn't talk discussion of this wall function today, but usually we are using a standard wall function for us to solve most of our problem. But we need to know the standard wall function still have some problem. For example, it's only based on the simple high Reynolds number flow. Yeah, for the lower Reynolds number effect, it doesn't work very well. But the good thing is for general environment turbulence is a very high Reynolds number, so that's fine. So this means standard wall function can use by us, have no problem. But in some transition state, for example, the flow is relatively small, or for example, it's a very small very small wind, but we have more convective terms. In this scenario, the wall function we need to help using the standard wall functions. Okay, let's talk about the grid mesh a little bit. For example, for the work functions, you can see here. So because we are talking about the work function, means we are using the log law. Talk about log law. So this means the first grid point should be in the log layer. So at least for the first grid point should be in the y plus in the 50 to 500. If your first grid point is inside this less than this grid value, means okay, you are predicting a large drag than it looks like. So we cannot represent it very well. So at least the 10 points in the boundary layer, and it's better to use a stretched coordinate or something. And for the two-layer model approach, this is similar as what resolved large estimation. So usually we want to the first grid point at the y plus roughly equal to 1, and there are some 10 grid points within the buffer and sub layer, and better to use the stretched coordinate to represent it. So most important part in this slide is talking about if we are using a large estimation and we are using work function, we need to make sure the first grid point is in the log layer. So the position is very important. We have the it's turbulent core, buffer, and sub layers. So if we are using one model, usually first grid point in here. So when you conduct simulation, it's very important to check the location of first grid point and also your grid resolution. Yeah, I think this is what I have today. And if you have any questions, we have further discussions.
Thank you.
Thank you.
So, Chief,
any questions?
Yeah, there's a chat. I see someone is chatting box. Give me a second. Okay. No question. Yeah.
No questions. So if we have no questions, we will yeah, so this will be our third lecture then. And so yeah, we'll be uploading the slides, right?
Yeah, I will uploading after the class. Yeah.